Hello everyone, welcome to this video. I will be discussing to you the classifications and biochemically important monosaccharides. In my previous video on stereochemistry, we have learned what it means by chiral center. And we know that a chiral center is an atom that has four different groups attached to it. So in this particular example, we can see that the second carbon in this molecule has four groups, different groups bonded to it. Okay, while on carbon number 1, there are only three groups bonded to it. So this is considered as one group, another group, and then the molecule or the group of atoms here. Whereas the second carbon has four different groups: the OH group, the hydrogen group, and then the molecule, the atoms here, and then the atoms below. That's why the second carbon is a chiral center. Now, this molecule here is known as glyceraldehyde. And glyceraldehyde is classified to be an Aldo triose. Remember, when we say aldose, this is based on an aldehyde. The functional group, okay, right here, this group here, as I have explained before, this is an aldehyde. So that's why this is an aldose. Moreover, it has three carbon atoms, 1, 2, 3. This is the third carbon, that's why it's called triose. All in all, glyceraldehyde is an aldo. Let's remove this. Let's drop the SE and then add triose. Okay, so the word is aldo triose. An aldo triose has one chiral center. Okay, the second carbon is the chiral center. That's why it is known to be N is equal to 1. Okay, where N is the number of chiral center. Now, in order to determine the number of possible enantiomer, we're going to use the formula 2 raised to n. Remember, n is the number of chiral center. So an Aldo triose has one chiral center. So if we put 2 raised to 1, then we get 2. An Aldo triose has two possible arrangements. If we are going to arrange the atoms in Aldo triose, we will come up with two possible arrangements. And we will see that in the coming slides. An Aldo tetrose has 4 carbon atoms. 1, 2, 3, 4. An Aldo tetrose has 2 chiral centers, being carbon 2 and carbon number 3. That's why we get N is equal to 2. Following this formula, 2 raised to N, where N is equal to 2, then therefore we say 2 raised to 2, then we have 4. An Aldo tetrose, the atoms of Aldo tetrose can be arranged into 4 different molecules. Likewise, an Aldo pentose has how many? 3 carbon atoms. So if we put that in the formula, 2 raised to 3, then we say we'll have 8. Okay? And the Aldo Hex Sources that have 4 chiral center, if we put that in the formula, 2 raised to 4, then we have 16 possible arrangement. So if we are going to arrange the atoms, the hydroxyl groups particularly of Aldo Hexose, we could have 18 or 16, sorry, 16 molecules, so 16 different molecules. So this is now the arrangement, the possible arrangements of molecules based on the formula that we have obtained earlier. A glyceraldehyde that has one chiral center, which we said n is equal to 1, and then we applied that into the formula of 2 raised to n. So 2 raised to 1 is equal to 2. So for an aldotriose, there are two possible arrangement of atoms. Okay, so what are those two? Okay, for glyceraldehyde, there are two possible arrangement. One is the D-Glyceraldehyde, and the other one is the L-Glyceraldehyde. You remember the difference between the D and L? Okay, in the D-Glyceraldehyde, you notice that here the OH is at the right side, or dextrorotatory. The mirror image of D-Glyceraldehyde, as we have learned, is L. All right, so if we put this OH on the left side of the molecule, so let's try to draw. Okay, this is the glyceraldehyde having the OH at the right side. This is denoted as D-Glyceraldehyde. Now, the other arrangement is if we put this OH at the left side. Alright, so we will have what we call L-Glyceraldehyde. So these are the two arrangements that we obtained from the formula. So again, let me label this as D enantiomer, and the other one is L enantiomer. Okay, for the Aldo Tetroses, remember in our previous slide we said that an Aldo Tetros has n is equal to 2. So if we put that in the equation or in the formula, 2 raised to n, then we say 2 raised to 2, then we have 4 possible arrangements. So what are those 4? 4 arrangements of molecules or atoms in molecule. So here we have 2 examples of D, being the D-erythrose and then the D-triose. Notice the difference between the D-erythrose and D-triose. On the second carbon, the OH is at the right, but here the OH is on the left. Okay, carbon number 3, the OH is on the right side, here at the right also. So we have already 2 D's, okay, plus, so we write here 2D, okay, plus the 2 mirror images of the D, which are the L's. Then how many? All in all, we have 4 molecules. Okay, so the mirror image of D-erythrose is L-erythrose. The mirror image of D-triose is D-triose, or sorry, L-triose. That's why all in all, there are 4 possible arrangements of atoms, okay, that we can produce in an Aldo Tetroses. Okay, the molecules that belong to this category, aldopentose, how many carbon atoms? There are five carbon atoms, and there will be our N now becomes 3. N is equal to 3. So that means in an aldopentose, there are 3 chiral centers. There are 3 chiral centers. They are carbon number 2, carbon 3, and carbon number 4. So if we put that in our equation, 2 raised to 3, if you recall, that would be 8. So an aldopentose, the atoms of aldopentoses can be arranged into 8 different molecules. So what are they? So we have here D-ribose, D-arabinose, D-xylose, and D-Lactose. So as you notice, we have here 4 D's, 4D, and if you get the mirror images of these D's, so 4 D's plus 4 L's, then all in all there will be 8 molecules. Okay, 8 different molecules that can be formed, okay, out of an aldopentoses. All right, so right here below, these are Aldo Hex Sources. Aldo Hex Sources contain 6 carbon atoms, but there are 4 chiral centers in a molecule, just like what we have seen in the previous slide. So what are the chiral centers in aldohexose? The carbon 2, 3, 4, and 5. So our N here is N is equal to 4. So if we put that in the formula, 2 raised to N, where N is equal to the chiral carbon, so 2 is equal to 4, or 2 raised to 4 gives 16. Okay, so the atoms of aldohexoses can be rearranged to form 16 different molecules. So what are those 16 arrangement? 16 different molecules. D-allose, D-altrose, D-glucose, D-mannose, D-glucose, D-idose, and D-galactose, and D-talose. So there are 8 Ds here, okay, plus the mirror images of these 8 Ds, so we say 8 Ls, okay. The mirror images of 8 Ds are the 8 Ls. So all in all, the total is 16 different arrangement. So again, we call these Ls and Ds the enantiomers. For keto sugar, the same principle applies. However, for a keto triose, we see that there is no chiral center because the second carbon is connected to only 3 different groups, unlike in glyceraldehyde earlier that we have seen, there are 4 different groups. So this is considered as one group, another group, the second group, and then a third group. So anyway, if you can also say that this is one group, another group, and then this is another another group. So all in all, there are only 3 groups. So it does not satisfy our rule that a chiral center must have 4 different groups. So a ketotriose does not have a pair of enantiomer. So what's the example of a ketotriose? The example is dihydroxyacetone. This is actually called not D. It's called dihydroxyacetone. Dihydroxy because there are 2 hydroxyl groups. Okay? 1 and then 2 hydroxyl groups. Okay, so this is called dihydroxyacetone. A ketotetrose has only one chiral center, which is the carbon number 3. So if we apply this formula, 2 raised to 1, so there are 2 possible arrangement of molecules in a ketotetrose, which we can see in the next slide. Ketopentose has 2 chiral centers, the carbon number 3 and carbon number 4. By the way, we call this ketose sugar because they are derived from ketones. Remember the formula of ketones in our previous videos? A ketone has a general formula of R bonded to a carbonyl group, carbon, to oxygen doubly bonded, and then this is connected again to another R group. So an R group, as I said before, it's an alkyl group or the rest of the molecule. So this is the carbonyl group. Okay? In ketone, the carbonyl group is in between two alkyl groups or 2 carbon atoms. So this is the carbonyl group in between 2 carbon atoms. That's why we call this ketose, a ketotriose. Okay, this example here, the carbonyl group is in between still 2 carbon atoms between 1 and 3. All right, so as I said, a ketotetrose having 1 chiral center, so 2 raised to 1, so we'll have 2 possible arrangements. So a ketopentose that has 5 carbon atoms, but there are only 2 chiral centers. That's why here 2 or N is equal to 2. So if we put that in the formula, 2 raised to 2, 2 raised to 2, therefore there are 4 possible arrangements. Okay? And a ketohexose that has 3 chiral centers, so 2 raised to 3 gives 8. So a ketohexose has 8 possible arrangements of its atoms. So here are the family of keto sugars. Okay, so the example or the simplest example of ketotriose is the dihydroxyacetone. I explained that earlier. So there's no chiral center, that's why there's only one arrangement, and that is dihydroxyacetone already. A ketotetrose that has 1 chiral center, so 2 raised to 1 gives 2. So a ketotetrose has 2 possible arrangements of atoms. Okay, what are they? The D-erythrose, okay, D-erythrose plus the L-erythrose 2. possible arrangements of atoms. So what are they? How do we call them? The D-erythrose and the L-erythrose, we call them enantiomers. Okay, we call them enantiomers. Okay, again, when we say mirror image molecules, we call them enantiomers. So a ketopentose that has how many chiral centers? Ketopentose that has two chiral centers. So we say 2 raised to 2 gives 4. There are 4 possible arrangements in ketopentoses. What are they? The D-ribose, D-ribulose, and D-cellulose. So here, 2D plus the 2 L's equal to 4. So if we put this OH at the other side, then we'll have L. If we put this OHs of ribulose to the other side, then we have L-ribulose. If we put the OHs of cellulose to the other side, this being transferred to the other side, the OH here being transferred to the other side, then we will have L-cellulose. Okay, for the keto hexoses, for a keto hexose, there are 3 chiral centers in the molecule. Okay, as we have seen earlier, where are the 3 chiral centers? The third, the fourth, and the fifth carbon are the chiral centers. So if we put that in the formula, 2 raised to 3 gives 8. Okay, so what are those 8 arrangements of molecules? D-cyclose, D-fructose, D-sorbose, and D-tagatose. So we have 4 D's plus. If we get the mirror images of each of these D's, then we will have 4L. So 4 D's plus 4 L's is equal to 8 arrangements of molecule. So how do we know the structure of L-cyclose? You just have to place the OHs of these molecules opposite to its direction. So if it is at the right side, then we put at the left side. Okay? If the OH here is at the left side, then we put at the right side to get the mirror image or the L enantiomer. Alright? This time we're going to encounter the biochemically important monosaccharides. There are several of them, namely the D-Glyceraldehyde and the dihydroxyacetone, and they are considered as the simplest monosaccharide. We have seen the structure of D-Glyceraldehyde and dihydroxyacetone. So they are actually important intermediates of glycolysis. Glycolysis is a reaction or a pathway where glucose is converted to pyruvate. We will see that in the coming presentation. So here you have again the structure of glyceraldehyde. This is an aldo. Glyceraldehyde is an aldotriose, whereas dihydroxyacetone is a ketotriose. Okay, and then we have here the 2 enantiomers of glyceraldehyde, the D and the L. Okay, our reference is the OH on the second carbon. Okay, If the OH on the second carbon is at the right, then we have a D, enantiomer. While if the OH on the chiral carbon points to the left, then we have an L, okay, L enantiomer. The second important molecule biochemically is the glucose. Okay, we will talk about this in the coming days. Dextrose is also known as, or glucose is also known as dextrose. The word dextrose comes from the property of the glucose that it rotates the plane polarized light, just like what we have seen in the previous video on stereochemistry. D-glucose is capable of rotating the plane polarized light to the right. That's why it's called dextrose, dextrorotatory. Okay, dextrose or dextrorotatory sugar. This is the main sugar in the blood. Okay, that's why it's called, also known as blood sugar. So here are the different picture of glucose. The alpha D glucose, and the other one is beta D glucose in Howard form, close Howard form, or cyclic. Okay, and then we have here the open chain or open projection. You call that Fischer projection. The difference between beta D-glucose and alpha D-glucose is if the OH on carbon number 1 is at the same side with the carbon number 6. Okay, that's beta. Whereas if it is alpha, if the OH in carbon number 1 is opposite with the carbon number 6. This is carbon number 6. The group here is carbon number 6. Okay, and if the OH in carbon number 1 is at opposite direction, or in other words, if the OH in carbon number 1 is downward, then we have an alpha. If the OH on carbon number 1 here is above, then we have what we call beta. Galactose is another important monosaccharide. Galactose is synthesized from glucose in the mammary glands for the production of milk. Galactose is a component of a molecule or sugar called lactose. This is the structure of lactose. Lactose is a combination between galactose and glucose. But this time in lactose, they are connected. They are connected by a bond. Galactose is also present in the chemical markers that distinguish various types of blood, the A, B, and O. As you notice in this picture, the galactose, the number of galactose molecules in different blood group differs. Okay, in AB there are 3 molecules. In some blood groups there are 2 galactose molecules only. Then we have fructose. Fructose is a keto hexose. We know what is ketose, sugar. It has 6 carbon atoms. It's also known as levulose or fruit sugar, and it's sweet compared to glucose. Okay, this is the Fischer projection of fructose, and this is the Hayward projection, or the closed chain or the ring system of fructose. Okay, And another one is ribose or D-ribose. A D-ribose is a pentose sugar. Pentose that has 5 carbon atoms. Okay? It's a component of the ribonucleic acid, RNA, and it's also component of the ATP or adenosine triphosphate. So this section here, this molecule here, is the ribose.